Let's turn attention to a second example. Here we will introduce how we treat inhomogeneous terms in the equation. So we are going to illustrate the method of variation of parameters using this example. The equation is written here. It's familiar to us from before. Second derivative plus gamma times first derivative plus the function itself equals now some right-hand side f tilde of tau. Remember, this was the scaled version of the mass spring damper system that we had previously looked at for the homogeneous problem. And so here now we have an inhomogeneous right-hand side, or a forcing term. And to make the problem specific, we can introduce initial conditions, and these are the same initial conditions that we had before, that the initial displacement is actually should be 1. I will fix this. So the initial displacement is unity, and the velocity at time equal to 0 is 0, and we are interested in solving that equation subject to these initial conditions. And there may be some prescribed right-hand side. Some forcing is prescribed. For example, we can think of that forcing as turning on at some time t equal to 0, staying on forever, or staying on for some finite duration t0, and then switching off. Those would be two particular types of forcing, or it could be some completely arbitrary function with arbitrary variation. As long as it's a prescribed variation, that would be a legitimate right-hand side. So for these cases, we can mathematically describe these functions. If it is a function which is turned on and becomes unity at time t equal to 0, that function is a step function, a unit step function, also called a Heaviside function. It takes on the value 0 when t is negative. It takes on the value 1 when tau is positive. And this is a composition of two Heaviside functions, or two step functions, one positive step function, one negative step function. The negative step function starts at tau equals t0, and so overall it results in this blue function which has a finite duration of length t0. So we can consider any arbitrary right-hand side function, and that is what we want to illustrate, how to do that. And so the step would be to start with this idea that we have talked about, that the solution is composed of a homogeneous solution plus a particular solution. And so the idea is we want to use a construction like this, and we propose that the particular solution is made up in terms of these known linearly independent solutions v1 and v2, but we multiply this first homogeneous solution by an unknown function a1 of tau, and we multiply the other by an unknown function a2 of tau, and so together this is the form that we would require of the particular solution. Note that we have two arbitrary functions here, so we have lots of degrees of freedom here to choose from, and in fact we can show that this is sufficient to be able to solve a general second order linear differential equation. So the object next is to find a procedure, a systematic way to finding these two arbitrary functions. So the method for finding these two arbitrary functions proceeds as follows. We have proposed the form for the particular solution, and we want to substitute this form in the differential equation. So we begin by taking the derivative of the proposed form. So first derivative of the particular solution, we can expand the product by product rule, the proposed form, and so we are going to get 4 terms. The product of a1 times v1 when differentiated, first taking derivative on the v1, next taking the derivative on a1, which is an arbitrary function, and likewise when we have the product a2 v2, a derivative here on v2, and then here the derivative on a2. So looks like we have sort of made life messy by having a whole bunch of 4 terms now, but we can make judicious choices here to simplify this expression. So just rewriting the equation above, a1 v1 dot, this first term, and the third term, we put them together, and these two second and fourth terms are written over here. And since we have two arbitrary functions to choose, we can always choose these functions so that this combination here with the curly bracket, we can set it exactly to 0. And why do we think we have this much freedom to do this? Is because suppose there is some way we find a1, then we can always choose a2 so that we can zero this out. And so we can rewrite this expression, putting this equal to 0 into an equation for A2. A2 dot equals, moving the other coefficients to the other side, minus V1 over V2 times A1 dot. So if we have a way of finding A1 dot, we substitute that in here and we'll be able to find A2 by solving this equation. And so we want to, once we have made this vanish, Vp dot is now just the product of just the sum of these first two terms. See that Vp dot is made up of this unknown function times V1 dot and this unknown function times V2 dot. It's interesting that this is the form that we had proposed for Vp itself, and now after taking derivative, the same products appear with the first derivative. And so that's how we can choose the function so that we have the simple rule for the first derivatives. Now we take the second derivative, so again applying the same procedure, we have four terms here, and the terms involving A1 dot and A2 dot are things that we can rewrite again. And so rewriting this expression here, A1 V1 double dot, A2 V2 double dot, and it's this combination involving the derivatives of A1 and A2. But A2 dot from this equation in the box has already been chosen, so we substitute that in here. And so when we substitute that, we can see that this expression amounts to nothing else but this product A1 dot over V2 times this quantity here, which is negative of the Wronskian. Remember that when we talked about linear independent solutions to the second order differential equation, we encountered this Wronskian of the two linearly independent solutions V1 and V2. And when they are linearly independent, then we know that this Wronskian is not equal to 0 identically over the interval. It may vanish in some place, but it doesn't vanish everywhere, and so on. So we have this expression which we can then use. So the next step would be to substitute the expression for the particular solution, its first derivative and its second derivative in the differential equation, and then we will see how to determine the unknown coefficients that we have here. So we're turning to that now.